S to recognize the language ATM. And we'll reduce that to the problem, or language, the problem of deciding ETM. Alright? That's our task. That's what, you know. It wasn't spelt out by Sipser. That's one of my major complaints of his approach. He leaves so much between the lines, which is not helpful. I mean, it's fine if you're an MIT student, 160 plus IQ, you can probably do that sort of thing yourself with ease. But for most students, that's, you know, it's unhelpful that these gaps exist in his text. I hope this feedback gets back to him sooner or later. Because God knows how many people are going to see this video over the next century, which is something else I'm highly conscious of. Whatever I say is forever. It's forever. Right. So thinking real time here. Okay, so we're going to reduce the problem of recognizing ATM to the problem of deciding ETM. Right? Now, we have a solution to deciding the language ETM, and that is the use of Turing machine R. Okay. That's assumed. That we began with that in proof by contradiction. We assumed the opposite. Hence, there is this machine R that can decide. Okay. So that's the solution. That's your problem B, in a sense, that we have a solution to. Okay, we have the solution. Solution is the existence of this Turing machine R that is capable of deciding ETM. Okay. Now, if we can reduce the problem A, which is how to construct a larger Turing machine S that recognizes ATM. Okay, so if we can do that, then we're fine, because then we've reduced problem A to problem B. In other words, we've reduced the problem of recognizing ATM to the problem of deciding ETM. Okay. And if we can do that, so if we can construct S using R, R is the solution to problem B, and we can use the solution to problem B to help us solve problem A. So in other words, the Turing machine S will use the machine R. Okay. And so we will then construct this Turing machine S, that recognizes ATM. Well, there's the contradiction, okay? Because we know, prior knowledge, that the language ATM is undecidable. Recognizable, decidable. Oh, no. Machine S, its job is not going to be just recognize it. It's to decide it, I think. Let me just check. Yeah, machine S will decide ATM. Okay, and we know that that's false. We know that ATM is undecidable, and hence we can then. So we know that problem B, language B, is undecidable, and language B in this case is ETM. I hope you followed all that, which is not spelt out explicitly in the text. I'm giving it to you now, quasi real time. Right? All right. So the problem now boils down is how do you reduce problem of constructing S to the problem of deciding ETM. We have a decider for ETM. It's the Turing machine R. Okay, so we'll use that. We will construct S that calls on R to help it do stuff. So what are we going to do? So we had machine R. Now, machine R decides this language, right, by definition. So it will accept. So it'll accept these every string. If it decides a language, every string that belongs to the language is accepted by the decider, by the Turing machine, and every string that does not belong to the language is rejected. Right? That's the definition of a decider. Okay, so so S will import something of this form. Okay. Ordered pair. So the angular brackets means an encoding of information about two things: the machine, just some Turing machine M and some string W. Okay, that's what goes in, and the Turing machine S, this bigger machine, it can extract two bits of information, and it can construct a machine, can simulate a machine M and some string W, and this is being done by Turing machine S, which is I guess that's why it's called S, simulator. Right. Now, machine M, from the discussion in the proof idea, that was not adequate. We had a problem. I won't go into all that again. So we modified the machine somewhat in such a way that we put a kind of filter in front of the machine M. So S will simulate this machine M, but it will add a kind of filter to M. So when a string goes into it, that filter will block it. It will block all strings W going in except that particular string there. Okay, and from the reasoning of the proof idea of the previous board, go back or look at the text if you rusty on it or you had trouble with it. Then this modified machine M, if you like, with a filter that filters out all strings W coming in except this one. This is the only one that gets through, right? So that machine that consists of this machine plus the filter, call that machine M-M1, right? Okay, so here's a description of what machine M1 does. So M1 is effectively this machine plus the filter. And the filter filters out all strings except this one string W, and that allows you to get around the problem we had in the proof idea. Okay, so here's the description of M1. It'll be a modified Turing machine. M's a Turing machine, so M1 will be a Turing machine. So here's the usual in standard notation. So